Alright, in this video I just want to talk about a couple of further details that we didn't get to in class about the definite integral. And I want to begin just by reminding us what this thing represents graphically. So the definite integral has these limits of integration from a to b, and again what these things represent are our starting point and our ending point for some function f of x, under which we are interested in finding the area. So this red shaded region, whatever that ends up being, this is the answer to this definite integral. That is what this thing is representing. It is the precise area underneath the curve from A to B. And one of the things that I want to get to in this video is this idea that the definite integral is representing the signed area. And what we mean by the signed area is that the area above the curve is positive, or sorry, above the x-axis is positive, and the area below the x-axis is considered negative. So if we look at this function and let's see, a is here and b is here, and I were to ask you to find the definite integral of this function f of x, I tried to draw this so that these two halves are the same. This region and this region are the same size, only we're going to consider this this first region to be positive because it's above the x-axis, and this second region to be negative. So if this was our function, the answer here would be 0. The area underneath the curve is 0. All of this is essentially canceling out all of this. So if we're looking at this function y equals negative 2x plus 2, we have a straight line with a slope of negative 2 and a y-intercept of 2. And if I wanted to find the antiderivative, or the integral, between 0 and 2, which graphically I would be showing here's 0 and here's 2, I want to find the area underneath this curve, which would be this. And this, and by the way, I could do this without any calculus, right? I could just find the area of these triangles using 1/2 times base times height. It's pretty quick and easy. 1/2 times base times height would be 1/2 times 1 times 2, which is 1. And then this triangle has the same, the one down here has the same area of 1, but it is a negative area, and we can actually prove this. If we use our skills that we looked at today in class, and we take the antiderivative here, I'm going to begin by raising my exponent by 1, and then my coefficient would be negative 1 plus 2x. And if I antidifferentiate this between 0 and 2, I can use my fundamental theorem of calculus. Again, we're going to talk more about this, but just as a sneak peek here, I can plug 2 in, and then I can plug 0 in. And this is going to equal 4 times negative 1, which is negative 4, plus 4. And all of this goes to 0, and negative 4 plus 4 is equal to 0. It works out. My point is proven that the area underneath the curve of this straight line between 0 and 2 is 0. Alright, I also want to mention in this video the integral of a constant, and what's going on with the integral of a constant, both graphically and algebraically. What this is saying, so a constant here could be like 2 or 10 or pi or 4, and graphically we know that a constant is a straight horizontal line. So this green line is my function c. It could be at a height of whatever c is, right? So what I'm doing here with this definite integral is I am attempting to find the precise area underneath the curve from A to B. And this is like the easiest thing ever, because the area underneath this curve is not even really the area under a curve, it's the area under a straight line. So the shape that I am generating here is a rectangle. So if we think about what this distance is, it's the distance between A and B, which is B minus A. And if we think about what the distance here is, that is the height of whatever this function is, and this function always has a height of C. So the area of this rectangle is C times B minus A. And we can confirm that using what we know already just about taking antiderivatives here. If I were to take the antiderivative of some constant, it would be Cx. And again, I can check that. I can take the derivative of Cx, and the derivative of Cx is equal to C. If you don't believe me with C, take a look at a number like 4. If it's 4x, the derivative of 4x is 4. In the same way, the antiderivative of 4 is 4x. So that's what I'm showing here with this Cx. And again, just from the end of class today, we talked about what's going on here with this evaluation bar between B and A, and I would evaluate this by finding C of B, or C times B, minus C times A, which hopefully you agree is the same thing as this. If I were to distribute that, I would be getting CB minus CA. So just to help us further develop our understanding that the definite integral is the area underneath the curve from one limit to another limit, let's look at this example. I want us to together prove that the definite integral from 0 to b of x is equal to 1/2 times b squared. So let's go ahead and look at this function that is the function x. That thing is a straight line going through the origin with a slope of 1. And I don't know what b is. It's going to be some number. I'm going to just put it right there, and I want to find the area that is this triangle. And again, this is sort of like the other example that we saw. We can find the area of this triangle using 1/2 times base times height. And this works out nicely because due to the fact that this has a slope of 1, up 1 over 1, we know that the two sides of the triangle are the same. So if this is b, this is also b. So we have 1/2 times b, which is 1/2 b squared. So graphically, that's giving us some sense of understanding. And we can check this again using our definite integral definition that we looked at in class. I can antidifferentiate x to get 1/2 times x squared and evaluate this between 0 and b. And when I plug these values in for x and subtract, I will end up with 1/2 times b squared. This whole second chunk goes to 0, and this is my answer. The area is 1/2 b squared.